Good morning, everybody. Welcome to Life Sciences Grade 12. My name is Duduzile Gupega. The topic is still on evolution. Remember, we had started discussing the theory, speculation, hypothesis. Now we're moving on to a model. Model is a representation, usually on a smaller scale, of a structure or process. It assists us in better understanding the phenomenon by providing an analogy. And when we discuss that model of the archaepteryx, right? Remember, and then the models that we have of the DNA helix, we have various models. We have the model of the dinosaurs. We have very different models. So those ones are representations, and they're done on a smaller scale, obviously, because we don't have a model as very large as a real dinosaur, you understand? So we make them on a smaller scale just to give us a clear picture of a structure or a process. And because of the models, we are better able to understand that phenomenon by providing an analogy. So whenever you see models, it's just that. And then a principle or law. A principle or law is an explanation with a great amount of supporting evidence, and it has been tested. I don't know what this is. It has been tested thoroughly with input and scrutiny by others. It works in almost all testable contexts. So whenever we speak of a principle or a law, we know this one has great amounts of supporting evidence. Great. And there is what? Supporting evidence. So you don't just have a principle. It takes a long time for for these processes to go through until it becomes a principle or a law. Understand, like the Newton's law, you understand? Those have been tested, and now there's evidence. And it's not just the person who came up with the principle who has provided it. It's people, different people who've come, who've tackled that and who've tested it, and it works. And then after that, it is passed on as law. Like the law of gravity, Newton's law, you know, all of those laws, they've been tested. And then now on to the historic overview of different theories of development. We know we are still on the topic of evolution, right? There are very different theories of development that from a very long time ago that different scientists had proposed as to how the changes on Earth began. So we need to understand life, and in order to understand life, we need to understand those early ideas as well, so we can track and see how far we've come. Since the earliest times, people have asked questions about the world and nature in order to make sense of it and understand it. The theory of spontaneous generation was formulated by cultures in Europe. So it was, you see, theory of spontaneous generation. It was formulated by cultures in Europe. And then this scientist here, Flemish chemist, he was a chemist, right? Flemish chemist Van Helmont, from the years 1577 to 1644, wrote this classic expression of spontaneous generation as capturing what people understood and accepted. If you press a piece of clothing soiled with sweat together with some wheat into an open mouth jar, after about 21 days, the odor changes and the ferment coming out of the cloth and penetrating through the husk of wheat changes the wheat into mince. So this is his classic expression of spontaneous generation. And you can see it, you can test this yourself. It was his way of trying to explain what this concept of spontaneous generation occurs. So you can take it, try it at home as well. Take a piece of clothing, soil it with sweat together with some wheat into an open mouth jar. Then after 21 days, monitor it and see and notice how the odor would change and it would ferment. Notice that, and then you'll see the wheat changing into mince. Try it and you will see. Then in the early 19th century, biologists started discovering fossilized life forms. More and more fossils were discovered, and scientists established a geological scale of periods in the Earth's history, arising from the depth of the different layers of the Earth. So you can try that, and you see that's why they found the different. After that early 19th century, more and more fossils were found. And then that's when they were able to start establishing the geological scales. And then, they would study these different layers and went in depth with all these layers of the different layers of the earth. And that's when we discovered the advancement of this study advanced even more. One such scientist was Adam Sedgwick. His studies on fossils led to his understanding that the earth was extremely old. So you see, as they studied fossils, he discovered that, you know what, based on this fossil evidence, you can deduce that the earth is extremely old. And this was in 1785. So if this scientist saw that in 1785, earth was extremely old, then it means now we can really believe it is extremely, extremely old. If in 1785 it was extremely old. And that had a series of great catastrophes had wiped out most of the life forms at various times during the Earth's history. So basically what it's saying is, the Earth as we know it now hasn't always been like this. There were species that existed during that time, various life forms that existed that we have never even known about. That's how big the earth is, and that's how old it is. There are species and species, different types of organisms that existed long before we came, that even died and went extinct long before we came. So the earth has been evolving ever since. It has been changing ever since. Even now, we have organisms we still have not yet discovered. That's how great the earth is. That's how big, and I mean, it's so big it can hide things in it. So till this day, we cannot know. We really wouldn't know. But he discovered this around 1785. So get that, like imagine, it was old. So it's very, very old. This scientist Cedric believed in divine creation that occurred over long periods of time. Again, you see that divine creation now? It occurred over long periods of time. So that's what he believed. And he also understood that some sort of evolution has taken place because there were organisms that had existed long before he came, and they even died long before he came. And then there's another scientist here who was a French scientist, Georges Cuvier. He studies the anatomy of living things, and he compared them with fossils in an attempt to understand how these organisms lived and why they died. Among others, he studied elephants and mammoth fossils. So in 1769 to 1832, that's when he was born and passed. One of his studies involved elephants and mammoth fossils. So he would study living organisms and then compare them with fossils that they found. Then mammoths, I have an image. There is a mammoth there at the top. You see, it's quite similar to an elephant. Look, even the husks and the trunk, it's very similar to each other. Mammoths are animals that became extinct thousands of years ago. But look how similar they are to elephants. Their bones are very similar to those of elephants, and they lived in very cold areas, such as Siberia and Alaska. So mammoths were living in very, very cold areas, such as Siberia and Alaska. So how did they know this? They discovered their fossils. They studied those fossils as well to understand these organisms. Cuvier showed that fossils were not just the remains of current living species, as many people believed, but that many species of living organisms had become extinct somehow. So before, they actually discovered that it was organisms that had lived long ago. When they studied these fossils, initially they had believed it's fossils from organisms that are still living, that are initially they believed that it's fossils from organisms that were still alive. So you know, when maybe an elephant dies and then they find their fossils, you know, they thought maybe it's a difference of like a few years, whereby you still have those species still alive, and maybe there are other family have died probably a few years, and then we discover the bones. That's what they initially thought. Like now, if you were to find bones of an elephant, you'd imagine it's because this elephant is, we still have those species, so it's easy. But then as they studied more fossils, they discovered that they are finding fossils of organisms they themselves had never even seen. And those organisms died long before they were even born. So that's what the discovery brought up. And then they could be found as fossils and contributed information to the fossil record and records of change in living organisms through the history of the Earth. The comparisons of the fossilized organisms were made by scientists and largely based on body forms and phenotypes. So body forms and phenotypes that could be seen from parts or whole structures that we found. So when you see a body form, that's what determined it at first. The comparisons are based on phenotype. Phenotype is the appearance, of course, how, what you see. You see the big ears, like those types. That's the phenotype. And the body forms as well. They would base it on that. They would compare it on that. So it wasn't that deep that they would maybe study the genetics. In the beginning, they didn't start off by studying the genetics of these organisms. They were just studying things they could see, or the whole structures that were found. Like I showed you, the mammoth over here and the elephant. How do mammoths and elephants compare with each other? How do they compare? You can compare it yourself and see, but look at the ears. That's the first structure. Ears are quite small on a mammoth, but elephant has very big ears. And then the trunk here. Elephant trunk. The mammoth one is very long, but the elephant's one is not that long. You see? But the structures are pretty similar. But an elephant is quite big even at the behind, yeah, but the mammoth is smaller. But we can study more and more and look at the legs. They're so not very similar to an elephant, but it's the same. Like if you were to find the fossil record of a mammoth, it might pass off or you might confuse it for an elephant until further studies were done and found that these are actually different species. And then now there's another scientist who was called Lamarck. I'm sure you've heard about Lamarck. His full name is Jean-Baptiste de Lamarck. He was a French naturalist. Again, this happened around the 1700s, you see. He was one of the first scientists to propose that organisms undergo change over time as a result of some natural phenomenon rather than divine intervention. So he was one of the first to discover that, you know what, these are actually different species. So clearly these organisms have undergone changes over time. And he explained that change is due to a result of a natural phenomenon, as opposed to just a divine intervention. And his theory is called Lamarckism. What did he explain? According to Lamarck, a changing environment causes an organism to change its behavior, thereby using some body parts more and others less. So that's his theory. Yeah? Saying a changing environment will cause an organism to change its behavior. So when it's changing its behaviors because of this changing environment, you will use your certain body parts more and other body parts less. And then over several generations, a given body part would increase in size if it was used a lot, or it will shrink if it was used less. So according to his theory, if we were to compare it with what we've learned so far, remember when we learned about the vestigial features, that would probably explain that maybe what our fused bone in human beings, over time we used it less and that's why it shrunk in size, you know, things like that. So That's how he explained it. This is the most popular theory or example he proposed, that of a giraffe. How has the giraffe adapted to its environment? You see the very long neck? He suggested that the giraffe got this long neck by straining to reach the leaves in a tree. And those characteristics were passed on to the offspring, which by continual stretching extended them even more. So he proposes that before, a giraffe had maybe a smaller neck, and then over time, because it was using its neck more and more, because it needed to get to the trees up there. So maybe in the beginning, he's thinking the tree or the food the giraffe was eating could be found below, just on the ground. But then as the trees grew in height, the giraffe needed to stretch to reach that food. And that's why eventually the giraffe ended up having a long neck, because it then went on to stretch and stretch and stretch until its offspring ended up having long necks. But this change obviously explains happens over a long period of time. So it's not something that happened over just a few years. No, it happened over probably centuries. So if you're to study fossils of giraffes from many centuries ago, you'd find necks, smaller necks. So that was Lamarck's theory. That's what he proposed, right? That is called Lamarckism. What is Lamarckism? It's an explaining that a changing environment causes an organism to change its behavior, thereby using some body parts more and others less. And then over several generations, you see, a generation takes a very long time. A given body part would increase in size if it was used a lot, or shrink if it was used less. So when asked about Lamarckism, this is what you explain, the part of underlined. And the example is that of the giraffe. So you can look at other various, maybe you can even pass that on to other organisms that have similar features, and that's how we try to explain it. Then we have another one that made his own suggestions. It is called Darwinism. This theory of natural selection is called Darwinism. It was made by Darwin. Darwin made it clear that in order to survive in an environment, an organism needs to adapt. For example, animals living in mountainous areas need to have claws or hooves to grip the rocks on which they climb. Otherwise, they can sustain serious injuries. This, the whole process of Darwin's theory, which is natural selection, will be discussed more in the next unit 2. Ne? So we'll discuss this in more details. But that's basically it. When you're asked about Darwinism, you need to explain that it's adapt or die. So if an organism cannot survive, and if an organism wants to survive in the changing environment, it needs to adapt. It needs to adapt to such environments. And then if it doesn't adapt, it would die. And it's quite similar. If you look at it like that, it's quite similar, not exactly the same. Please remember that it's not exactly the same. It's a little similar to what Lamarck proposed, because according to his theory, if the giraffe had not if the giraffe had not really, okay, we are explaining this the phenomenon of the giraffe, but according to Darwin's theory. So using Darwin's theory, you would say the giraffe wanted to survive because its food now was on the high trees, né? And it had a short neck. So in order for it to survive, it had to adapt to a longer neck structure so that it can reach that food. As opposed to Darwin's theory, where it says you need to continuously use that feature, and then if the one you use less, then it will shrink, the one you use more will stretch. So based on the Lamarck, actually, what features in your body do you use more than others? Then test that. What features do you use more than others? And then if you were to apply Lamarck's theory, we'll find that some of you wouldn't have hands anymore because you don't want to use your hands. You wouldn't have your legs anymore because you don't want to use your legs. You don't want to walk. You don't want to, you just want to sit. Some of you wouldn't have brains anymore because, I mean, at school, you don't even want to think sometimes, you know? So according, we thank God it's not according to Lamarck's theory. And then there is what we call as well as what we call punctuated equilibrium. Whereas Darwin, his full name is Charles Darwin, whereas Charles Darwin saw evolution as a slow, continuous process without sudden jumps. Scientists like Eldridge and Gould observed that evolution sometimes happens very slowly and sometimes very rapidly. So Darwin believed it happens slowly and continuously over a long period of time. But these ones then, who are called who? We've got Eldridge and Gould. They observed that evolution sometimes happens very slowly, so they agreed with Darwin in this part. But they also believe that it can happen very rapidly too, and that is called the punctuated equilibrium. Punctuated equilibrium is a theory of evolution that states that most species will show very little evolutionary change for most of their geological history, remaining in a state of stasis. So that's what he believed, that if over time others, they wouldn't change. When you look at them, you'd see little change over a very long period of time for most of their geological history. So that means they remain in a state of stasis. So imagine if you can't observe any changes in these, and the environments are changing over time, then really these theories are, they quite differ from each other, all of them. And then if we study a cladogram, the rapid evolution phase is represented by the branching off when a new group develops. So according to that theory, an organism or species wouldn't change over long periods of time in their geological history. And then there'll be a sudden change whereby an organism, a different organism, will just branch off from it suddenly. And then we'll look at the cladogram. What is a cladogram? You will get cladograms a lot, especially in your papers where you asked to see, like, determine who is the ancestor of this one, there'd be different types. Cladogram is a diagram used to represent a hypothetical relationship between groups of animals, which are called a phylogeny. How you represent that hypothetical relationship. A cladogram is used by a scientist studying phylogenetic systemics to visualize the groups of organisms being compared, how they are related, and their most common ancestors. Now, I didn't hyperlink this. Let me do it now. I want us to go to this. It's on Google. Yeah, hyperlinked now. I want us to go view this. A cladogram, just images of cladograms. You see cladograms there. You'd get this, you'd get such in your papers. Let's look at this one. You're trying to find the common ancestor. You see, you're looking at these, you're looking at all of these features. Then you'll study it. These are typical examples of cladograms. There'll be a session where we learn about cladograms in full, so you can fully understand exactly how to work it out, so that when you get such and you're asked which species are closely related than the others, you can be able to answer that. Example, this is a more simplified one. You can see that A and B's common ancestor is here at this point here. And then A and C's common ancestor is here. You see? But they are common ancestors. You see, you can just study this. A and B, it branched off over here. There's the common ancestor. Then you go further back in the geological timeline, you find that main ancestor, the first ancestor for these three species originated from here. And then it formed this one organism and that other organism. It formed this organism that then led to who's the common ancestor for B and A. And that one, this one here, the common ancestor for B and A is closely related to C. So you understand? So maybe how can I put it? This is you are the kids. Ne? These are your parents. Then C is your mother's, this is your mother, this one. Then C is like your mother's sister. Yeah, typically, but we'll have a session dedicated on that. and you'll be able to understand this better. So don't worry about it. Okay, next up, what time? We still have time. Yes, we have time. The development of a modern theory of evolution. Now we have this modern theory of evolution, right? Many people contributed to the modern theory of evolution because these people, it was mostly scientists in the 1700s, right? We've just seen them and studied them. They had different proposals, different theories as to how evolution occurred. Ne? Now, all of those ideas put together informed what we call the modern theory of evolution. But we need to see who are those people who contributed to our understanding of evolution, because you can clearly see there are different points. It almost makes sense, all of them. You understand it somehow. You agree with bits and pieces of what they proposed. And that's what formed today's, which we term as the modern theory of evolution. But who are the people who contributed to our understanding of evolution? These are the people. At the top over there, we have Erasmus Darwin. Erasmus was the grandfather of Charles Darwin. He influenced Charles's thoughts on evolution. We have John Baptiste de Lamarck. Who is Lamarck? Who formulated Lamarckism, that theory where he proposed the idea of use and disuse of inheritance of acquired characteristics. That one of the giraffe, whereby it says if you use one part less, then it will shrink. The one you use more will increase in size. Then we have Thomas Malthus. He stated that poverty and starvation were consequences of overpopulation. So poverty and starvation are consequences of overpopulation. Herbert Spencer proposed the concept of survival of the fittest. So you see this, I've only in school, I always thought the survival of the fittest came with Charles Darwin. It actually came with Herbert Spencer. He proposed the concept of survival of the fittest. Alfred Russel Wallace formulated the theory of natural selection. So that of Herbert, survival of the fittest and natural selection, they link up with each other, hence the arrow over here. And then those two, Herbert and Alfred, meaning survival of the fittest and theory of natural selection, then are linked directly to Charles Darwin's theory of evolution. Thomas's theory as well of poverty and starvation being consequences of overpopulation linked directly to Charles Darwin. So most of them link to Charles Darwin's theory. And then Charles Lyell, who has a major influence on Darwin. So you see, Darwin was like, he really did study. Charles Lyell had a major influence on Darwin. He proposed that the earth is much older than people thought. Darwin studied that. So Darwin studied all those different theories from different sciences before he formulated his own. So he gathered all those ideas from people, and then he tried to make sense of it, like how we are agreeing with bits and pieces of that. He did the same. He saw that this one makes sense. He took that, adopted that, and then formulated a whole study. August proposed chromosomes as basis of heredity. And then R.A. Fisher explain that population genetics and mathematical aspects of evolution. Then we have Gregor Mendel. We will study a lot of Mendel when we do genetics. If you plan on doing a career in genetics as well, you'll study more of Mendel's theories. He developed the fundamentals of the genetic basis of inheritance. And then we have Julian Huxley, Ernest Maxey, and the Theodosius. All these three, they incorporated developments in genetics, paleontology, and other branches of biology. So all of these, at some point in your life studies in the sciences, you will come across these scientists and study their theories in depth. Here it's three of them. It's Fisher, it's Haldane, and it's Wright. All of those put together, they contributed to our understanding today of the evolution. The new synthesis is the neo-Darwinism, which is a version of Darwin's theory refined in the light of modern biological knowledge. So we wouldn't know what we know today if it was not for the contributions of all these other scientists. We wouldn't have, we really wouldn't know. Even Darwin himself wouldn't have proposed his theory if he hadn't studied the contributions of the other scientists. So one way or the other, they influenced each other. You see, with Alfred was influenced by Herbert clearly as it connects. So one way or the other, these scientists influenced each other. So we really can't give credit to one scientist if we're being fair, because they all contributed to the study. If it wasn't for Spencer proposing the concept of survival for the fittest, Alfred wouldn't have proposed the theory of natural selection. You see? And then Darwin wouldn't have proposed that theory of evolution by natural selection. So you see how it links. If it wasn't for Erasmus's influence on Darwin, then who knows if Darwin would have even come up with this theory. If Lamarck hadn't proposed his theory of use and disuse, who knows how Darwin would have maybe sieved through those ideas. So we owe it to all of them. The understanding that we have today is based on their great work. So, yep, guys, this is an activity. We will do this tomorrow because we won't have time to finish today. We'll start off tomorrow's lesson. We will start off on this activity before moving on to other work. Now, guys, we are going to wrap this up tomorrow, and then we'll do other activities. I want us to be able to apply what we've learned in the activities. And it's also really my aim to prepare you for your exams so that you are ready. I want you to be ready, and we need you. We need you to get good marks. Even with all the challenges we are faced with currently, we still really want you to do well. Work is accessed from the Via Africa Life Sciences Grade 12 Learners Book, which I access from Stapify app. And then the pictures we saw there, I included the hyperlink, which took us to that site. And for more information, here are the links you could go to. Thank you so much, everyone. Bye.